Saturn's satellites, including Titan, provide clues to planetary formation. Titan formed from the same protoplanetary disk and later collected debris forming its thick atmosphere. Cassini's Huygens probe revealed mountains shaped by erosion and rivers flowing not with water, but with liquid methane. Titan is one of only 2 places in the solar system with precipitation, Earth being the other. Titan's extreme cold, 290 B's, challenges Earth-like life, but molecules like vinyl cyanide could form cell-like membranes capable of surviving in the frigid environment. Titan could therefore host alien life, resilient in ways we are only beginning to imagine. Early Earth collided with a planetary body named Theia, a monumental event reshaping our planet. This collision ejected more than 1 billion tons of debris, forming a disk that eventually coalesced into the Moon. The impact merged Theia's iron core with Earth's, enlarging our core and sustaining a magnetic field to protect our atmosphere from the Sun's charged particles. The Moon also stabilized Earth's rotation, creating tides and slowing the day to support life. Without this lucky collision, Earth might not have developed the conditions necessary for life. Earth's orbit around the Sun is not static. Slight variations in the orbit's shape, influenced by the Moon, other planets, and Jupiter's gravity, can trigger ice ages. Around 15,000 years ago, lowered temperatures trapped water in glaciers and ice sheets, lowering sea levels and forming land bridges for human migration. Earth's orbit is also part of a larger galactic journey. The solar system orbits the Milky Way at roughly 537,000 miles per hour, completing a full orbit every 230 million years. The Sun's path is not flat. Its mass distribution creates oscillations, carrying Earth through different galactic environments approximately every 60,000 years. Building a planet is not simple. From dust grains to planetesimals, each step takes time. Jupiter, for instance, had to wait for distant rocks to collide and merge, a process that could take 100 million years. But young stars cannot support disks indefinitely. They emit intense radiation and solar winds. The protoplanetary disk lasts only 4 to 5 million years, meaning planets must form quickly. To capture nearby gas, a protoplanet must rapidly form a solid core. Adding pebbles to planet formation models accelerates growth. Small pebbles provide substantial mass for growing protoplanets. Once a planetesimal forms, it doesn't need another to grow. It can feed on surrounding pebbles. Its gravity captures nearby material, increasing growth speed. The first protoplanet to grow quickly can dominate its region, starving smaller neighbors of pebbles. This explains how outer gas giants like Jupiter formed so quickly. Pebble accretion allowed their cores to capture gas before it dispersed. Numerical models show this process can form giant planets in just a few million years. Mars lacks a substantial atmosphere because, without a protective magnetic field, it has been continuously stripped away. Solar winds can erode the atmosphere. On Earth, a molten metallic core generates a magnetic field that protects the planet and helps maintain the atmosphere. Mars, however, is different. Formed 4.5 billion years ago from space dust and gas, it grew in a region with scarce building materials, stunting its growth. This is why Mars is much smaller than Earth, about 10 times smaller in mass. This mass difference matters. Earth's extra mass keeps its interior hot, generates a spinning core, and creates a magnetic field. About 4 billion years ago, Mars's turbulent heart cooled and solidified. Without a hot core, no magnetic field formed. Solar wind has slowly stripped away Mars's atmosphere, leaving it thin and inhospitable. NASA had to get creative to land unmanned spacecraft on Mars. In 2012, the revolutionary Sky Crane lowered the Curiosity rover using parachutes and retro rockets. Earlier missions used airbags and inflatable devices, but astronauts would not want to bounce on airbags for a landing. Human Mars landers will require new techniques. NASA's next rover, launched in 2020, used a supersonic parachute inflation research experiment. While this worked for the rover, human landers are heavier and require different strategies. Ideas include using Mars's thin atmosphere creatively, approaching rapidly, gliding in the denser lower atmosphere, and finally using landing rockets to slow descent. Even with successful landings, Mars's dust storms are another danger. Dust can rise and remain suspended for long periods, creating massive storms that block sunlight, cool the surface, and drive winds stronger. NASA's Opportunity rover, experienced the perils of these storms firsthand. The farthest point a human has ever reached from Earth requires extreme precautions. When NASA astronauts arrive on Mars, they will face enormous challenges. Landing on the planet is a difficult task. Mars has never exactly rolled out the welcome mat for spacecraft. In fact, sending something from Earth and landing it on Mars is incredibly hard. The European Space Agency had hoped that its $250 million Schiaparelli lander would touch down successfully in 2016. However, the landing systems failed. The parachute detached too early, and the craft plummeted freely for 33 seconds, hitting the surface at 335 meters per second, leaving a deep black mark. Mars proved to be especially difficult for landings. Even humanity's brightest engineers have only about a 50% success rate for Mars landings. The red planet is littered with failed probes. NASA must learn from these mistakes for its first crewed Mars landing. But as the astronauts descend, they face the same problem as all previous failed landers. The Martian atmosphere is 100 times thinner than Earth's, providing insufficient friction to slow down a spacecraft. Unlike Earth, with its massive parachutes, to slow landers, Mars offers limited atmospheric braking. ALMA Observatory has provided a clue. In Titan's nitrogen and methane-rich atmosphere, sunlight can break and recombine these molecules like Lego blocks. They can then form new molecules, such as vinyl cyanide. Artist's depiction, music vinyl. Cyanide can form long molecular chains capable of creating cell membranes, something necessary for life. Unlike Earth's water-based cells, these membranes could survive the extreme cold. Music. It can survive at these low temperatures, so on Titan, vinyl cyanide could potentially form membranes necessary for cell development and life itself. And the good news is that there is plenty of it on Titan. One single lake contains as much as 10 billion tons of vinyl cyanide. If you wanted to make creatures from it, say giant squids, well, you could make billions of giant squids from this vinyl cyanide. Do you like giant squids? Hopefully yes. Just as we know life could exist on Saturn's geyser moon Enceladus, there could truly be life on Titan. Titan is a relentlessly cold and harsh place compared to Earth, but it might be ideal for titanic life. When searching for life beyond Earth, we face a bias based on life as we know it. Expanding our definitions and approaches as we explore allows us to better understand where and how life could exist. Perhaps there are 2 living worlds in the Saturn system. But on Titan's surface, life would also need to survive deadly particle storms from the Sun. Traveling more than 1 million miles away, 20 years after Voyager, the Huygens probe launched from Cassini plunged into the dark depths of Titan's atmosphere. The first images of the Titanic landscape were truly mind-blowing. Music. They revealed mountains with what appeared to be erosion, as if some kind of liquid had flowed down their slopes, carrying material along. This liquid must have come from somewhere, and on Titan, it could only come from precipitation, rain caused by the atmosphere. There are only 2 places in the solar system where rivers and rain exist, Earth and Titan. Within this dense gloom, Titan is the place that most closely resembles Earth, similar, but not the same. The lakes and rivers on Titan are not filled with water, but with liquid methane. Imagine if every oil well and gas station on Earth leaked everywhere. This would be the result. On Titan, methane is liquid because the surface temperature is around 90 K, 290 degrees, which presents a major problem for life as we understand it. No organism we know of can survive at such low temperatures. Our Earth-based cells, made of proteins and lipids, would simply stop functioning and die.